Thank you very much. Good morning. Pleasure to be here. We kept on this conference. I'll focus this talk on the Dark Energy Survey, a talk on behalf of a large collaboration. But I'll also try to take you a bit beyond it and to comment on the next generation of surveys and possibly what are the interesting questions ahead. The outline of the talk will discuss the current landscape, although we have excellent talks, past 2 days, summarizing it. Some results from today's survey, early results, synergy with other surveys, testing gravity by combining imaging and spectroscopy. That's a theme of interest to many people here. We'll have some talks about that. But then I'll also talk about the nitty-gritty of this subject, the painful points, nuisance parameters. So it becomes from freak. We may have great vision to measure tiny effects, but then they might get worked out by marginalization or systematics. So I wanted to bring it up front rather than hiding. Just quick thank you to collaborators. I work in kind of two circles, two overlapping circles. So there is the group at University College London. We are now head count. Oh, thank you. That's better. I think there are some 34 cosmologists now at UCL, 5 staff plus postdocs for students. And then there's the larger circle of the DES collaboration. That's about 300 or so people here at the collaboration building in Barcelona. There are a number of DES collaborators here, including Dave Bacon and Ramon Miquel, who will also give a talk about DES tomorrow. So what is dark energy? This is a mixed audience of theoreticians and observers. I think it's all disturbing. When I was a PhD student in Cambridge, lambda was categorically 0, and everybody spoke with the same level of vigor as they speak now about lambda, about the universe with lambda equals 0, 5% baryonic matter, 95% cold dark matter. So myself, I'm waiting for the next paradigm shift. It's getting a bit boring, and but nevertheless, here it's the phase space, so you know the latest data illustrated here in the W0 omega curvature, including more or less on W of -1, which corresponds to a lambda universe. The number is actually technically less than -1, which is not so physical, but I guess it's just systematics. And that's the latest from Planck plus Bose. You see improving on the universe with lambda and 0 curvature. But we don't know. Who knows? Maybe systematics just mimic dark energy. You're all being fooled by the data. Maybe it is, after all, the equation of state of -1, lambda CDN model. Maybe it's a dynamical scalar field, W Z. And we'll parameterize our ignorance by putting W0, WA. But who knows what it is really. Modified gravity. We heard some possibilities about that. In homogeneous universe, we know that X is only an approximation. So surely it goes all the way to people who claim maybe we live inside the void. That's an extreme statement, but in any case we already admit that we live in a clumped universe. Some people find it a bit too restricting to live only in one universe. So they look for a multiverse. And it's a way out of thinking about these funny universes. I was in Madrid in the conference of philosophy of science. Robert Ellis was there. There was a lively debate about the universe, multiverse, many philosophical problems. Maybe something else unpredictable. The Planck press release came up with a statement. The ESO ESA press release said an almost perfect universe, which I don't quite understand. I think I can relate more to the New York Times, who said a simple but strange universe. So I think that's more the state of affairs. Good zooming in on those values, almost to the level it's becoming boring, but still a long list of scenarios there. And of course, there are GR people here, so I'm going to elaborate on this, but this question, is this lambda on the left-hand side or the right-hand side? Right? Is it just quick curvature, or is it a part of an actual mu, an actual substance? Trying to get some help from my talking to philosophers and historians of science. This is an article I wrote with Michela Massimi, or a historian, she's a philosopher of science, and we just wanted to draw attention to mention on the, by David, on the first day, about the analogy, possible analogy, dark energy and the ether. So I'd like to talk about something a bit more concrete, because I think we have a very nice illustration within our solar system that there is a possibility of a new entity or a new theory. So if you like, it's the left-hand side, sorry, it's the right-hand side or the left-hand side, if I refer to it as that. And the example is the discovery of Neptune, which of course was a result of looking at the orbits of Uranus and noticing they are perturbed. And two theoreticians independently, Leverrier and Adams, came up with the idea, well, let's put another planet there, right? So it's like dark matter particle, if you like. And indeed, Neptune was discovered. I think it's a beautiful example of that. First, less known is that Bessel actually suggested an astrophysical explanation, right? He tried to go around, just like we heard yesterday in Romel's talk, trying to find astrophysical solutions to problems. He tried to find an astrophysical solution, which didn't work, so brackets is at least it didn't work. On the other hand, in our same solar system, the example of Mercury's orbit is just the other example, that in fact, Leverrier suggested another hypothetical planet called Vulcan, which was never discovered, and instead it was a new theory that solved the problem. So I think when you look at the accelerated universe, we're still in this problem with only dark energy or modified gravity. Right? Is this the right-hand side of the equation or the left-hand side? And the other similar examples, of course, with flat rotation curves, where the majority of people think it's dark matter, Mikron, Bekenstein, and others suggest modification, and of course with the neutrino it's also a similar interesting example. So there are examples of history that show you one or the other, we don't know the answer yet. Just before we talk about the big survey and how we do them, just a little bit about a bit of intuition about cosmological constant or some other forms of dark energy. So in the Newtonian limit to GR, we know we can write the acceleration as 1 g over r squared plus the linear term in r by weight. Some little known fact is that Newton actually also talked about the linear force. We just didn't call it lambda over 3 before, so that's another interesting point. But we just ask ourselves, at what scales would lambda be important? So is it important on solar system? Well, I'm sure you've given that problem to your students, and the answer is no. But it turns out on the scale of the local group, it's quite important. Actually, I was surprised when we did this calculation that actually, if you put lambda in, you find for the total mass of Andromeda in the Milky Way a mass which is 13% higher than in the absence of lambda. If lambda is giving you a push. It's actually 13% effect. So if you like, we do have an evidence of lambda even in the local universe. We've actually, in the process of using simulations from Cruz, from Stefan and Hoffman and others, Yetes here as well, from that team, to actually look into this and check the validity of this timing argument that is called M now, but also to really see if indeed we can improve on that mass estimate. So it's just one conclusion lesson to take home is that even on the megaparsec scale, there's some imprint of lambda. Now to the big picture of surveys. This is focused on the optical surveys. Of course, there's this fantastic activity of SKA here and around the world, and you heard about it. But it's basically the community, or rather the US funding agency, divided into stage 3 and stage 4, and both were already results. I'll talk about our survey. There's some other projects going on, including e-bots, which we'll hear about later. The Japanese hypersuperprime, followed by the spectroscopic one, headlights, and so on. And there's the next stage, which is DESI. I'll talk a bit about that, the dark energy spectroscopic instrument, not to be confused with DES and there's DESI. Euclid, LSSP, and maybe US satellites, and of course all the activity in the rest of it. A lot is going on, billions of dollars, but it will produce billions of galaxies, so I like to tell funding agencies to get a galaxy for only $1. Good bargain. Okay, so dark energy survey. I was fortunate when I moved from Cambridge to head the group in UCL, and we looked for started cosmology from scratch, and we looked for activities beyond 2DF at the time. We just 2DF then just came to an end, and we were fortunate to talk to colleagues at Fermilab, and we got there quite at the beginning, and we worked both in both instrumentation and in science. So this is, for those not familiar with it, this is using an existing telescope, so there was no need to build a new one. That's the Banco telescope in Chile. It's a 4-meter telescope. But in order to do wide field imaging, of course, it required an optical corrector and building your camera with lots of CCDs, and that's why it has taken 10 years to get there, right? So that's even an existing telescope, just building an instrument these days. Yeah, getting the funding and actually getting to work is not 10 years. Luckily, we had the first light in September 2012, first season already behind us, and we're now in the midst of the second season. Just some numbers. There are two modes here of the wide. It's a wide field survey of 5 times 30 degrees, which will combine measurements of clusters, counts, weak length, and larger structure. I think it was among the first surveys to think, let's not do just one thing, but do multi-probe approach. And then there's a time domain, which is looking at relatively small fields, 30 square degrees, and supernovae. Hopefully, it will be 4,000 or so supernovae per day. And the wide field will produce about 200 million photometric redshift. I should emphasize it's a photometric redshift survey. A good thing, you can collect many galaxies, but you still have to estimate the photo Z, and that's of course a challenge, but we also have many spectroscopic data, lots of spectroscopic data in parallel. Lots of overlap with the VISTA hemisphere survey, with the SPT, South Pole Telescope, and we get spectroscopy from OSDES, EBOS, etc. Year one aimed at 2,030 degrees at 40% of the depth. You can see here the success rate. We can see not bad. It's close to the 0.9 arcseconds for weak lensing. And now, at the midst of year two, we're aiming at 3,000. So, if you like, after 2 years, we hope to get the full area at 40% of the depth. Okay? That's the idea. It's a big collaboration, 300 scientists from 6 countries. When we started, we were small, it's growing and growing. I read in recently interesting number called the Dunbar number. What's the maximum number of collaborators you can have? What is the cognitive limit on how many collaborators you can have? And it's 150. Now this magic number comes by scaling it relative to the way chimpanzees interact with their mates. And if you extrapolate the size of the brain you find that it's about 150, and then you look at government, financial organizations, universities, it's about right. It's about 150. So we kind of slightly too big now, but of course you benefit from that. I will talk to colleagues from LHC, Euclid and so on, where the numbers are much bigger. But it's interesting to keep it in mind. As a remark, I'd also make a remark, recently co-supervised a master's student, Lucy Calder, who looked at the anthropology of the dark energy sector. She looked at us, how we operate as a system. And it's a highly nonlinear system, which includes noise and other effects. But on the whole, it's a happy collaboration, 6 countries. I think it's going well. George Freeman is the director, founding director of John Peoples. Brandon Flowers led the instrumentation. There are obviously all the different tasks, quite complex, and I think, on the whole, I think it's functioning well in terms of the work at the telescope, the data management, which is done in Illinois, and of course the science. The science is coordinated by this committee, which I co-chair with Claire Bernstein. There are 12 different working groups. I think there's a similar pattern now on most of the big surveys of this type of topics, which is core dark energy, but also other things such as Milky Way and quasars and galaxy evolution. So I'm sure you all know that culture, of telecoms and meetings, but it's been very exciting bringing theoreticians and observers, also people from energy physics, astronomers, over 6 countries. It's been a very interesting experience. Now, it takes time, of course, to build it. We're fortunate that our instrumentation team, led by Peter Dole, here by student Mitch, we're fortunate to get funding straight at the beginning from our funding agency, SDC, to build the optical corrector. There are many, many other steps, including the filters, for example, were made in Japan in a factory which is somewhere there, just about 100 kilometers away from the center of the tsunami. So, nevertheless, they managed not only to get on time, but even the filters are better than what was expected. And, well, you put all these things together and worry for 10 years, and then you point a telescope and see different galaxies. So that's a short summary. This was the first slide in 2012. These are the 62 CCDs. In this case, pointing to the 4X cluster, and this is this galaxy, the Glisti galaxy. And the nice thing is, the images were quite, seeing was quite good actually at the start, and weather, of course, fluctuates, but on the whole, not bad. This is again for those who like to see the numbers, the wide survey, 5 times 12 degrees, in those filters, GRIZY, and then the supernova fields are shallow and deep. When the seeing is poorer than 1.1 arc seconds, the telescope looks at supernovae. So there's a whole strategy to observations. This is just the footprint. So the black line around is what the survey eventually will cover at 5 times 4 degrees. The red is actually some testing data for science verification. Those data are good enough to produce papers. Some of them are also page. And the blue region is the first year. As I said, the second year is to cover most of the remaining 3,000 square degrees. No time to go through it, but you see lots and lots of colors there. And these are overlapping surveys. So no, I think we cannot take the surveys these days in isolation, right? It's very important to have these other imaging surveys in other wavelengths, such as infrared, for example, and of course spectroscopy. Very, very important. So we have overlap, for example, with EBOS. And this is extremely important in order to calibrate the photoset. First images, you can see it's a camera, so you detect satellites, you detect near-Earth asteroids, Kuiper belt objects, just everything. but obviously also galaxies. Now, there's a lot of simulation effort done in DES, and you try, of course, to validate your science doing that, but whatever you do, you don't know what the truth is. So, luckily, for some fields, we have actually data from HST. So this is a clash survey of 25 classes in which I'm also involved, and with the students and we're actually comparing the two. Now, of course, this is spaces in the ground. So, of course, you can show it as great publicity for space, and that's what you can give. But at the moment, it's only over 25 clusters. So, the important thing is by comparing the two, we use that actually DES is doing just what it's supposed to be doing in terms of shape measurements and photo Z. Okay, so I want to emphasize that by comparing it with space data, we actually validated that those two important things is measuring shape for weak lensing, and photo Z seems to pass the test. I commented about seeing these are histograms, but number to take home is about, just short of just a little bit worse than the Scampanen. Okay, so it's about 0.9 seconds, which is of course the critical number for weak lensing. Highlights from the survey. Again, a lot is going on. There are papers on the Astro PH you can see, and we kind of Ramon and I divided the discussion of science between us. So he will tell you tomorrow about the detection of a superluminous galaxy, a supernova, but also hundreds of supernova 1A candidates. There is also a candidate, more than a candidate, it's confirmed, Quasar 36, many new clusters, mass maps which I'll show you, detection of galaxy lensing, correlations, which I'll talk a little bit about. Ramon will also talk to you. This is LMC, and hopefully the southern hemisphere, like that object. So, results from Dark Energy Survey about the LMC, and that's, I think, all a very rich package of results, and you're welcome to look at the papers. This is detection of clusters. This is done. Some clusters are known. We've seen this friend, the bullet cluster number close yesterday, but others are new clusters, so they get this DES name, and this is done by a technique called red matter, red sequence. I mentioned the overlap with the Vista Hemisphere survey. It's nice to see that DES and VHS see the same galaxies, and one can also do what's called forced photometry to know where the DES galaxy is, and you can just go to the Vista field and extract more photons, and that's what my former postdoc, Manda Banerjee, has done. And you can see that you improve the counts in VHS from being less dark to being the red curve, almost as much as you get down to K-band 23 or so with video survey. So I want to emphasize this synergy. Lensing, we heard a lot about this. The story is simple. This is by the way from Clash. You see this beautiful art there. It's already made it to a calendar for 2015, this picture. You can see how the bending between those two halos here. And as emphasized in talks past 2 days, the shear, the distortion, which is very pronounced in arcs, weaker in the field as weak lensing, it basically depends on cosmological distances and on the intervening mass. So that is two parts of the story, the intervening fluctuations and the geometry. And that's how you try to get dark energy out of it. This is the first paper led by Peter Melchior, and what you can see here, the dots are galaxies, and the contours are actually mass maps. Okay, so this is using weak lensing to reconstruct the mass. This is the scale is changed, by the way, and here it's 2 megaparsec, here it's 5, and you can even see, you take a panoramic view, you can see the cosmic web. So that's I think, to me, a great moment that actually, after 10 years of hard work and worrying about optics and the filters and all that, is actually working, and you can get weak lensing signal, and you can get mass nets which look believable. Of course, there's more work to do to quantify, but it's kind of nice to see that light traces mass. It's some kind of gives us some confidence that we know what we're doing. Of course, with weak lensing, it's even harder. So here is my 1% rule for weak lensing with this. The distortion of an image is about 1%. And you want to measure it to 1% in order to get W to 1%. Is this okay? I can repeat that, but it's written there. So you can see how challenging it is. And you are aware of all these tests people have done, the step and grade, which I realize people now trying to apply for SKA. And this is, however, kind of a proof of concept that you can do massive construction not only around us but also in the field. So what you see here is the following. You basically get what's called KE, which is the divergence of the kappa net. But this is essentially the distribution of mass. Of course, it's very noisy, but we believe there is something there, and then you can compare that to the distribution of galaxies, and with a bit of imagination, this is some distribution of galaxies involved in some way with a similar kernel. With a bit of imagination, you can actually look at this. You heard about it, feedback from David who's involved with that study, and we are actually collaborating on trying to analyze those maps produced by Dikram and collaborators. So I think the message here is dark energy survey has already seen dark matter, both in clusters and in the field. We're working on dark energy survey to actually see dark energy. That's a harder task, but as you can imagine, there are already preliminary Hubble diagrams of supernovae and some analysis which hopefully will help us to bypass this 1% rule and get into W. There is also quite a lot of activity on cross-correlating dark energy survey galaxies with other mass maps. For example, you can get mass maps from the CMB. So again, it's lensing of the CMB photons by intervening matter, and you can do that. So this is work in preparation by some of the collaborators, and you can see the galaxy-galaxy correlation function. So it's difficult to see, but it's an angle, and that's a correlation function, and you can see a well-known pattern with the biasing opportunity. But what's even more impressive, you can cross-correlate the galaxies with SPP, mass reconstructed maps, and you see a signal. It's weaker than Planck law. But nevertheless, this is a very, again, amazing confirmation that the galaxies trace the mass, if you think about it. However, we are in this funny situation. We have to deal with systematics. I like to call them nuisance parameters, depends how you think about them. I think they come in three flavors. There are theoretical uncertainties. In other words, you have freedom of what cosmological model to use. You know, with and without continuums, for example. There are astrophysical uncertainties, such as galaxy biasing, dust in supernovae, or induced economics weak lensing. Okay, these are astrophysical. Some people are more interested in those than in cosmology. They would like to know about biasing or the dust in both galaxies. And finally, instrumentation. Okay, so these are things we hope to control. Of course, for example, we're worried about the image quality, and seeing the turbulence of the atmosphere, but if you go to space, you bypass it. Okay? Or you're worried about photos but if you do spectroscopy, you bypass. Okay, so these are, I think, more control and hope that, you know, mankind can solve them. These are more fundamental to astrophysics, and this has to do with our perception of cosmology. So what they find is quite remarkable, that we seem to fit the whole universe with about 6 parameters. But we have about actually hundreds of nuisance parameters. if you count honestly how many free parameters are there in the analysis of Planck, and if you do the same with Dark-Energy Survey and Euclid and LSST and SK, you will find that actually hundreds of nuisance parameters. And some of them are dealt with in a very honest way by using other data. In other cases, it's not a matter of being dishonest, it's just they're done in, let's say, in a naive way. But I'm myself a bit concerned if we have so much faith in a universe with 6 parameters, but there are all these hundreds of other parameters floating around, how should we handle that? One example is star-galaxy separation. This is this LMC I talked about earlier. This is a patch of test, and you can see the challenge of actually telling what's a star of the galaxies. You can imagine in this patch, most of them are stars. This is a work led by a student of mine, where we try to improve on the star-galaxy separation. Stars are in red, galaxies in blue. That's one way of doing it. And this is another way using your network, so we try to separate them as much as possible. But that's an example of systematic. You wouldn't like to calculate correlation function of stars and deduce that we need to modify gravity, right? So one has to be very careful with this. I've been interested in biasing for many years, as many others in the community. And what has occurred to me, and I'm deliberately trying to be a bit provocative, is that there's a big gap here between the rich literature of biasing from simulations we heard from Brunel's talk yesterday and other talks about simulations. A huge effort, very fancy models of how to do good galaxies and feedback and so on. Then you look at the cosmology papers, and you see that people just assume biasing to be constant, or just assume biasing to go like 1 plus z. Why? In fact, biasing goes like 1 plus z is a model which is relevant in Einstein de Sitter universe. People don't even tell you that. So I have taken the step, here it's led by a PhD student, Clerky, we've taken the step to actually take the rich literature and try to translate it to a human language. And it's being inspired by forms of the period literature. It's not entirely original. We came up with this form for biasing, which is 3 parameters, but it seems to be in accord with the Halo model and the like. Okay, so it encapsulates all these other models, and we're taking our next step to do it for luminosity, class, and also to incorporate a K-scale. I don't have time to talk about it, but this is W0WA, and you can see if you assume your own biasing, your ellipse can easily end up being far away from where it should be. Okay, so this is a classic example of nuisance parameter, and basically what I'm trying to say here is let's work harder to incorporate physics. I still believe that the more physics you put in, physically motivated models are much better than just, putting ad hoc models. Not only that, as a byproduct, you can of course get biasing by combining large destruction and frequency. This is a nice paper by Julio et al. And you can see the linear biasing becomes the spreadsheet, and the model we advocated seems to fit quite well this data. Of course, cosmology does not stop with dark energy. Neutrino mass is a very interesting target here. The current best numbers in the literature are the sum M1 plus M2 plus M3 is 0.3 eV. By the way, Planck has done wonderful things, but hasn't improved on that. So the papers that appeared 2 or 3 years ahead of Planck just came up with the same number. We use some PhotoZ catalog, the same number in other groups as well. With dark energy survey, the hope is, plus Planck, the hope is we'll get down to 0.1 eV. Remember, the bound from below solar atmospheric oscillations is 0.06. So, at some point, either we know what we're doing in cosmology, and we measure it, or we don't know what we're doing in cosmology. If we can't detect the neutrino mass, then we have to question ourselves, can we detect other things, right? To me, it's a good test of the validity of the model because we know it exists and there are lab experiments or ground-based experiments. And we're doing pretty well, and I like to tease my energy physicist colleagues. I say, with Capri, which is a beautiful experiment, we get 0.6 eV, we can get 1 eV. Things like Euclid, SKA and the like predict numbers 0.02, 0.05 or so. So I think it's going to be quite exciting to get actually a real parameter out of all these data sets. Next generation, we've seen some slides from Euclid the other day. This is LSST. So obviously we're going to a completely different regime. This is just a comparison. There's an LSST. This is a new telescope, of course, wider sky. But you know, the new flavor of the month is to talk about big data. So here's DES producing 1 terabyte per night. LSST will produce kind of the movie of the universe with 30 terabytes. DES reduced will be about 2-3 petabytes. LSST, SKA, etc. We're talking about hundreds of petabytes. It's all going to be a whole new regime. DESI is another project in which we're involved. There's already some support from the Department of Energy. It passed the critical stage, and also it passed the critical stage in terms of UK funding. We just heard good news about that. This is doing spectroscopy, so if you like, it's 10 times better than BOS, okay? In everything, in terms of fibers and in terms of performance on cosmological parameters, using, by the way, the twin telescope of the plant for the one in the north, the Kneib. Of course, the publicity diagram here is to get these little black dots on the Hubble diagram relative to the supernova and to get the BAO scale with 0.4%. But as commented yesterday, look, it's fantastic and we should be doing that. But at some point we'll say, well, we've seen enough of that. Is there new science? I'd like to mention, I was in 2DF for 10 years, and to the best of my knowledge, neither 2DF nor Sloan had BAO in their proposals. Okay, BAO appeared later. So that's true about all these surveys. It's great, we plan them with a very specific goal, and I think other branches of science are envious of us. Because we know we're looking for something and we see this diagram. But the nice thing is we can do other things with it. And I think the same is true with SKA and the like. So one example, we've seen this type of potential where we can use two potentials. This is an example work led by my postdoc, Dr. McCurk, how really by using weak lensing, which is the green curve, and the large structure, which is the solid curve. So weak lensing from DES and large structure from DESI, you can get the red ellipse. If you have them overlapping, it's even better. If you want to modify gravity, you see the performance is even better formally. Figure of merit goes up if you combine imaging spectroscopy by a factor of 170. Of course, figure of merit, you have to be careful how you do it, but there's clearly hope there. And the final thing, I'm essentially there. I just want to say, I'm very impressed in this conference, the first conference I've been to in recent years, where there's so much emphasis on relativistic effects in large structure. So we have very inspiring talks by Kemi and Ruth and David, and I know that Roy's group here is doing a lot of work on that. And so I've got interested in that recently, and that's work with Miftah Sadeh, another postdoc, and a master student, Feng, where we basically looked with admiration at this result by Voigt et al., where they looked at the gravitational redshift due to the difference in potential between the galaxy in the bottom of the potential well in the cluster, the BCG, and surrounding galaxies. And they found an effect of 10 kilometers per second, which is quite remarkable. And I thought, wow. And nobody repeated it. So there are all these theoretical papers by Kaiser and Peacock, and I said, wow, we must repeat that. And after lots of hard work, that's what we get. So if you go to the outskirts of the cluster, of course, if you look at the center of the cluster, of course, there's no effect. So photons from the BCG as a neighboring galaxy at the bottom will be redshifted at the same level. But relative to those at the outskirts, we also find similar effect. In fact, it comes to be same number, -11, +7, -5. That's using a much bigger data set from Sloan and Boss, and different techniques, lots of systematics, the papers on the archive. But to me, it's very nice to see actually a measurement of that, and all the talks and formalism we've seen. to apply to broader surveys, including Euclid and SKA, I think it's all very inspiring to start seeing all these effects. So I think this brings me to an end. The summary is DES-centric. Basically, DES is observing well after 10 years of preparations. We're now in the midst of the second year. I think we kind of proved this proof of concept that we can get photos and cost control at the level that produces science, already in papers on the page. We can see mass, we can see nice cross correlations with other surveys. And last but not least, I would like to emphasize, although the name is Dark Energy Survey, it produces lots of other science. And I recommend young people who join this say, don't just do W0, WA, look elsewhere, do other things with it. And I think there's a lot of scope, not only in neutrino mass, but Milky Way, quasars, galaxy evolution. And I think, if anything, in terms of DES itself, the next 3 years, and the next generation of surveys, stage 4, and the next generation of astronomers, is very impressive. I think the best is still to come. Thank you very much.
Time for questions.
Here is one. Oh, yeah.
When do you get the
Well, so there is already two-week lensing measurements. One is around clusters, and one is in the field. So there is a reconstruction of mass. But I guess you're asking when are we going to get actually W? Well, as you know well, it's about area. So I think probably year 2, compilation of year 2, we'll start seeing the two-point function and few parameters coming.
So how one is doing the star galaxy separation, because you don't have spectroscopy, you go deep, so your sources are point-like mostly, I guess. So is there an algorithm adopted by the team that works in this respect?
So I mentioned there are several algorithms. I showed you that this is, okay, so there are some algorithms which are kind of, this one is very nice actually, although it looks broad here. This was devised by, for spread model devised by Emmanuel Cortin. So it's just a statement about how spiky the object is. You know, we always use simulations to understand that if an object is spiky, you can tell if it's one or the other. In this work we've done using neural nets, we use a training set, and in part it's using real data, as you said, when you know pure spectroscopy, you know if the object is actually 0 or not. So we use part of that and also simulation. So it's a combination of data and spectroscopy, but of course, whatever you do, you end up with a probability. You'll never know for sure if it's one for magnitude, it's one or the other. It's probability.
Time for final question or comment. Please.
Just a little comment to your philosophical slide, because I like it. So will we ever be able to decide if it's a new theory or an additional ingredient, or left-hand side or right-hand side, to put a modification? Unfortunately, it's not really separable so easily, because very often when you change your theory, you just add a new degree of freedom. That's the least you have to do, whatever you do, if it's f of r or something like that. Typically, if it's a scalar degree of freedom. But once you have just a physical scalar and a physical graviton, you can always reformulate it as, just a new substance. So there is no real separation between new theory and new substance, unless you give really up basic things like diffeomorphism symmetry or this type of stuff.
Well, I think in certain framework, people are optimistic that they look at the growth of structure. They'll be able to tell one or the other. But I appreciate your point that you can always rephrase
structure. I've heard it often. That would be a sign for modified gravity. but it's equivalent to coupled quintessence. Just have quintessence scalar field also coupled to dark matter, and you get exactly the same. So there's a mathematical equivalence. It's simply not true that by experiment you can decide between modified gravity and a dynamical scalar field with coupling to dark energy, let's say. They are simply equivalent, unfortunately.
You're posing us a challenge. Maybe I'm happy to discuss it more from your perspective. I think there are some techniques to do it, but it's challenging. And who knows, time will tell if you're on the left and side on the right. Thank you.
Thank you very much, Lahav. We have the pleasure also today to host Kneib. We talk about measurements of the percent level of the dark.
Hey, it's a pleasure to be here. First time I'm coming to Cape Town for some time, so okay. So I'm going to talk about basically two experiments, but they all concern about person level measurement of the dark universe. So we all hear about cosmology and the measurement of the dark universe, and one key motivation for this on the direction side is to be as precise and hopefully as accurate as possible. So we shift to the description of cosmology as equations to something more accurate. So to go and probe this precision cosmology, I'm going to talk about two aspects. Measurement of dark matter in strong length clusters, and I will focus in particular on the Global Frontier Field project. And then I'll talk about large-scale structure relative survey that Olaf already mentioned a bit. And in particular, I'll focus on the Sloan 4 Eagle survey. So, as we just said, cosmology been moving quite a bit into observational-driven science with this big project that are gathering a lot of data. So we all know about WMAP, Planck, Factory, BOSS, just heard of ES, and there's plenty to come in the future. What we want to do is basically try to understand, these dark components of the universe, understand the nature. And one way is basically to have more accurate, more precise measurement. And so maybe then we can say something about the relation between dark matter and baryons. Maybe we can try to better understand the acceleration of the expansion, and we try to measure it not only today, but all over the whole time. And so maybe then we can say something about the evolution, maybe we can say something about the question of state, this dark energy, or we can learn more about what is gravity. So to do this kind of precision cosmology measurement, we need also tools to do that. And what I'm going to focus here is basically two different tools. And we develop on how we're going to use them, or we're starting to use them, and how when in the near future. So we need to do simple physical measurements. And there's two very good techniques to do that. I look at strong gravitational lensing, and I'll explain how it works a bit, and the Those measurements are interesting because in principle there is no systematic, also that they are sealed. At least they're supposed to be quite small. For example, for strong lensing, it's very predictive. Once you have a model, you can predict what is the contrary, what are the multiple images system, etc. So if you have a model, then you can basically make prediction and be sure that what you're measuring is what you get. And in case of BAO, then you have large statistic, and you have so much data, you can really try to understand all possible systems. So the two projects I'm going to talk about is double frontier field. So that's a dedicated survey with HST, and it's basically gathering a number of people. Okay. Let's see. It doesn't work since. Anyway, so we just had a very nice meeting last week in Yale with like about 80 persons really working on that topic. And the second group of people here, that is a picture taken in Utah last summer, focused on massive spectroscopic survey using the responsible collaboration. So first I'm going to talk about measurement we have done in the last 6 months, typically about the above frontier fields. And I want to thank all the people I've been working with that we call CAS team, in particular John Richard, Matthew Durack, Akimatek, So what are we doing here? We're looking at massive cluster galaxies in the universe. Those are very rare and unique systems, and typically you can find maybe one strong lensing cluster per 10 square degree in the sky. So maybe you have like 2,000 of them that eventually you can study, and probably only like 200 are really relatively well identified today. And maybe only like 20 are very good systems that have been observed, say, till last year or so. So what we have a very high concentration of mass in the universe that distort the space-time, and when you look through that massive cluster galaxy, you look at background galaxies, and if the cluster is massive enough, then you have multiple image system forming in the core of the cluster. And that's very simple because it's just gravitational optics. It does only depend on the mass that the light beam going through, and the distance, the relative distance of the source and the lens. So if you have a good model of your cosmology, because you need to be able to calculate the distance, and you have a good model of your cluster, basically there's no error in principle there. And just to have you an order of the size of the effect, for those most massive clusters, we're looking at area on the scale of typically 10 to 50, or basically 1 atom in scale. So because of those very nice systems, there's been recently what is called the ultra-deep urban imaging dedicated to survey 6 clusters. And we see 4 of them here. And we see a pointing centered on the cluster and one pointing centered on the, somewhere like 600 meters away. And you see 2 cameras. The blue is the ACS, the red is the Pic-Tree. And so here, on these pointings, there's 140 orbits of HST. 7 filters, so that allow you to make nice photos and also look at very distant galaxies. And all these clusters are very massive. It's been selected in X-rays and ranging from redshift 0.3 to 0.55. So the main focus of this program is essentially to look at very distant galaxy redshifts, up to 10 or so, and look at the evolution of release function, and look at high magnification sources that magnify that typically up to 50, so things that you wouldn't be able to see if you were not using those clusters as cosmic telescope. But to do these signs, you really need to have a good understanding of the dark matter in your cluster. And you have to do that at basically the percent level. Otherwise, you won't be able to compute the minimum function, you won't be able to tell that source is magnified by a factor of 50. So you really need to understand your dark matter distribution. There's all the science you can do, and in particular one that is interesting for cosmology is to do cosmography, and I'll say a bit more there. So the project is going well along. There's been big data taken. So there's 840 orbits in total. There's already almost like 40–45% of the data that has been acquired. The data become public almost immediately, like a week after or 2 weeks after observation. We have completely reduced data on the web, on the SDSI archive. And then you have people that are basically modelers that try to understand the mass distribution of the system. So to do the mass modeling, what you need to do is to identify the multiple images in this cluster, and I'll show some example. You need also to determine the redshift of the system, and ideally you want to complement this data set with other wavelengths imaging. So you have many follow-ups going on using weak-lensing, X-ray, SG, also measuring galaxy dynamics, and all these things are in progress. So you identify multiple images system in cluster. Well, they basically have same redshift, same color, similar morphology. They're distorted differently, so it's not exactly the same shape, but very close. But of course, if one image is forming an arc, then it's a bit more complex because usually only part of the image is a multiple image. So there's been a lot of work trying to detect those multiple images systematically, because you have a lot of light coming from the cluster, you want to remove that, and so there's been people looking at wavelength method, also like subtractive Canadian image, and so then you go find multiple images, put that in the model, refine your model, basically help you find multiple image system, and then you basically improve things to very high accuracy. And there's also people working on automated multiple image system finder, because at the moment mostly all things are done by hand. So this, so let's give you some darkness here. Not for very long, but just so that we can appreciate the data. So that's the data of MAX 4416, one of the frontier field cluster before the Hubble frontier field observation. At that time, there was only 34 multiple image systems found, and no cleansing data. There's been a paper explaining all that. And just before the observation, there's been more work to be done, and there's been found even more multiple images from the old data. So that's what we get. So things are getting more prominent. We're finding 194 multiple image systems, and basically that's the cluster which the best constraint ever in terms of strong density, or at least currently things really improve. Here, what you see, it's the cluster, and each of these dots here are system multiple image systems. So 154 targets. And that's just a zoom, and we see that we go very thin, so thin that properly you cannot see all the images. You can see the circle, but not the data, but if you really play with the data, you can see all that. And from that images and the measurement, you can build a model, and you see with the contours here, the mass reconstruction coming from the model. Okay. More light, you can appreciate more. So we do not only strong lensing, we do also weak lensing, and we have basically developed techniques that are joining strong and weak lensing techniques. It doesn't completely work yet, but we're making progress because those are two different regimes and you have to take the errors in the proper way so that your model doesn't favor too strongly the strong lensing or too strongly the weak lensing. But we're making good progress there. This is the mass reconstruction of the dark matter when you have both strong and weak lensing constraint. In this case, you don't not have just only the two central fronts, which were very prominent in a strong lensing analysis, but you also detect on the outskirts group scale structure that are also quite nice. But you're still kind of limited to the data right now because you only have basically these images and nothing around. You really want to expand on the larger scale. So things like DES or even more data from HSC would be helpful. To really scale things in terms of total mass, you need to measure the distance to the background sources. So you need to measure the distance to multiple HSC. But of course, as we're going very deep, spectroscopy gets to be very difficult. So there's basically two ways that are people thinking to do this measurement. One of them is using the Hubble Space Telescope with X-ray prisms, and here is some measurement of very distant objects that you can get with X-ray, typically measuring galaxies between redshift 1 and 3. Or there's a new instrument called the Muse FDLT, which is really a radiation. It's an IFU that can take the spectra of any object within 1 arcmeter square. And it's so sensitive that it's the best spectroscopic instrument by typically a factor of 2 in terms of throughput at VLT. And there's been a number of papers coming out, and even there's been recent observation of one of the cluster in a front effect cluster. And what's amazing is that you're able to detect Lyman alpha images of pairs of multiple images system that you don't even see in the Hubble frontier field data, which is one of the deepest imaging data you have. So this is very interesting, and it's a very good avenue of finding even more multiple image system at the redshift. So what we know about mass modeling? So that's a representation of different mass models coming from the different groups. So in red, in the color red is the magnification of the cluster. In blue is the dark matter distribution, and those models were done before the HFF observation. And what you see is that although there's some kind of rough broad agreement in terms of the shape of the amplification region, there's some difference in some cases that I've circled in red. So when we want to make comparison, that's something, a task that is to be done on the frontier field data. We really need to make a truth comparison, making like a figure of merit of the different models to make a comparison. The idea behind that is we want to improve the way people are doing modeling and maybe converge with one technique. To help that, people have been trying to put together a cluster modeling challenge, and that's here you have the all information to get to this data, and if you want to play with your mass model, or you want to build your own mass model, you can do that. There's been different kind of simulation done, from purely numerical simulation or from HOD modeling, and people have been trying to reconstruct the mass distribution of those systems. Interestingly, basically we are modeling systematic, we are modeling limited at the moment. So this is a result coming from the simulated data. So the good thing is that we know what we have in terms of mass, and we want to reconstruct that. Here, I didn't put the mass, but I could have in the mass too. I just put the magnification effect as a function of the number of images you have to reconstruct your cluster. And what you see is that as the number of multiple images increase, your error is decreasing, okay? But at some point you hit like a systematic error level. And this systematic error is basically a limitation in your mass model to reproduce the data. Just because you're using like the wrong assumption, you're modeling the cluster with some kind of typical mass distribution that where you basically build in some limits because you're using some kind of parameters and not others. So you, at some point, your model doesn't follow your data. So you're really systematically limited. And you do also see that in the backend, what we call the ERMS, but it's also somewhere an estimate of the cat-square of the technique, that basically your cat-square is improving as you increase your number of parameters. One issue is that you really need to have a correct identification of the multiple image system. And that has been clear in another cluster that has been observed by the Frontier fields. Before the Frontier field observation, we were expecting to see the contour image of the object 3, the image 3 of the system 3, so 3.3 on the top of there, but in fact with the new data we found out it to be like 10 arcseconds below. That's a huge difference, and of course that means you have a huge difference in mass estimate of your cluster, and that basically this effect, you can see it here, where you have the surface mass density of the cluster function of radius. Those two models are pre-HFF observation, and this one is with the correct identification. So not only you need to find the multiple image, but you need to find them correctly. And that, of course, that data will lead to very interesting findings, like this one, where we detect a redshift 9.8 multiple image system in 27.4. So the Frontier fields is a very rich data set. Most of it is publicly available. So there's a lot of people crunching the data and trying to do good science all the way. What we have obtained in the last months, basically, for two clusters, we have a current modeling that is below 1% level mass in terms of precision of the mass measurement. And that is possible because you have 150 to 200 multiple images per cluster. But we can do much better because the chi-square or the RMS value of the image position uncertainty is very large. We have an RMS value of 0.5 to 0.8, while HSC, PSF is something like 0.1 or so. So we can do much better in terms of the modeling, and we're currently limited by the way the models are done. So we really limited by our theory, by the way we're putting things together. So there's a huge step for improvement here, probably a factor of 10 or 5 or 10 better in terms of the image RMS. So that's maybe given us opportunity to do research, new discovery. So that's something that's interesting. So what kind of things we can do to improve those mass models? Well, we have this challenge about the mass modeling to improve the techniques, and I think that's a very good way to do that. And that means we need to think a bit differently, and really to include all the different components and really tweak them so that they really fit the data. There's different things in the mass distribution of the cluster. We have the large scale, but we have also the small scale, what I call substructure, which basically are galaxy halos, and we have also galaxy or structure along the line of sight. That's why I call the 3 events. We really need to model that too. And we need to have quite a flexible component for the cluster dark matter, or even the X-ray gas that sits in the cluster, because this is also a significant component basically working with like grid-based technique. And we can also, and we need probably also to include more constraints. Of course, there's multiple images, but there's also rephasing that are really important, especially if you want to see what's the distribution on large scale, and that does affect a little bit what's in the center too. We need spectroscopic redshift, and I just talked about a bit. So the use and the reference data. We could try to deflection, which is the way the galaxies are bent in the central part, so not just as an ellipse, but as a kind of banana shape. And we need to improve the modeling speed, because some of those codes are not very much parallelized, and they should be great. So what better models will value, and that's one example I'd like to push forward is we can probably do even more precision cosmology measurement. And that's from a paper of Eric Joe, one of my students, about 1689, where you can effectively, if you have very good mass accuracy, because you have lots of constraints, you can keep constraint on W and omega. This measurement was done with like 40 multiple image systems. That's what you expect to see with like 240 multiple image systems. That's from a simulated cluster. And here, that's also from simulated cluster. The relative error you will get on omega m and W by increasing the number of multiple image systems. Of course, that means that you really understand your mass model, and you're not limited systematically by the fact that you're too constrained in terms of the way the model is. But that's something that it's likely possible. So that's a quick conclusion of the above frontier fields, and I will move to the second part of the talk. So really, you could see that the above frontier fields as a revolution, but there's still lots of challenge and improvement to do. So stay tuned, and if people are interested, let me know. The other measurement I want to push here is the EBOS survey. So EBOS is relying on the VAO measurement, which originated from very early on in the universe, and you can see it in the planet data, and basically you can see it also in the galaxy distribution, because it's where the galaxy are forming. Okay? And so in those early high density of matter that just right after CMB, you form galaxies, and you see them basically up to redshift 0. And because you're doing a measurement on the direction, perpendicular to the direction of the plane of the sky, and within the plane of the sky, you'll be able to constrain two parameters of velocity, which is also interesting because you can correlate those two and you make sure that you have a good measurement. This is the VO measurement that you already have seen in the literature from both, and they're basically coming from a survey which is 1.5 million galaxies of the sky between redshift 0.2 and 0.6. Now we want to continue this survey, and that's the extended EBOS survey. So this is a survey that has been in preparation since 3 years ago or so, and there's been a number of tasks that has been done since then, up to very recently in July 2014 when the survey just started. And up to now, or at least 10 days ago, we completed like 70 EBOS plates, so imagining more than 60,000 redshift already, and we have a meeting in a couple of weeks, merging EBOS and EBOS calibration of the telescope. So comparing to both, which basically focus on relatively nearby galaxies, to redshift 0.6 or so. We want to go even higher redshift. And we want to do that using different tracers. We want to use galaxies and quasars. So we want to fill this space here between basically 6 billion years to 11 billion years, where there are basically no video data. And we want to basically trace the last scale structure in this space. Why we want to do that? I mean, it's usual things, as I say, dark energy, understand gravitation. We're going to put also constraint on neutrino mass and also possibly on non stability. So we have a different kind of probe, although video is like the main probe. There's a number of tests we can be able to use with this data to probe cosmology. There's also side signs that are going to be done using the quasar, because ultimately when EBOS will be finished, we'll have a catalog of 1 billion quasar. So that's quite an improvement compared to what we have currently. So we can look at limit sum function, we can look at the multiplicity patterns of the bytes, we can do plenty of things, look at physics by looking at the composite spectra. And there's also a small program looking at regression mapping of those waves. The third science driver is about the galaxies, because the survey will have an ELG and LRG mapping between redshift 0.6 and 1. So we really expand a redshift range, from basically 0.6 to 1 for the galaxy, and all over 3.5 is the quasar. So we're going to select those objects. The quasar will be selected with different technique. The main technique is using just photometry as the SSM-wise, and the other technique, the main technique, is looking at variability of the quasar. And that's what is summarized here. The new addition compared to earlier surveys is the use of the WISE data. And you see here a color plot of G minus R versus I minus Y. And what you see is the quasars are very located at a very different place compared to the star vectors. So it's very easy, if you had WISE, to select your quasar. The other selection technique is by using variability. Quasars are variable sources, and we've been using the parallel present factory data, and that's basically a map of all the sky covered by PTF. You have the Milky Way here, so there's not much observation. And then the color scale tells you how many observations you have from PTF. So the more data you have from PTF, the more variability information you have, and then we can really select those quasars. Those techniques have been basically validated by a program called Sequest using the Sloan-free project. So they were being done during this March, April this year. And we basically recover the redshift distribution of the quasar. We're going to target with EBOS. So you see we have bulk of the quasar just targeted by color up to redshift 2.5 also, and then we have the second bump coming from the variability. Here it's about the galaxy selection. Again, we're using WISE data to select red galaxies, and that's a good picture that shows you that LRG galaxies are becoming very bright in the WISE data. You do see that also in this color plot, R minus Y, R minus I, and you see that the high-redshift red galaxy sits in the triangle, so they are very easy to select. And we've been also training, doing test spectroscopy on both to measure the redshift distribution of those galaxies. We have a good redshift distribution center at 0.75, so really striving redshift 0.6 to 1. Same thing for emission galaxies. Emission galaxies are going to be the main system to be used in the future by DAISY or those future survey in 5 years from now, typically. And so we're basically starting using them in EBOS. You have two kinds of selection using U-band and SPSS data or using DS only data. And we basically are trying to decide in the next weeks which one we're going to use. That's the survey footprint. It's about 7,500 square degrees for LRG and quasars. And for ERG, we only cover the smaller field of view on the source scan. That's the data release plan. We're very organized. We only know when we have our cosmology paper coming out, so stay tuned. Be patient. And that's the forecast in terms of accuracy, precision measurement we expect to reach. For the LRG, we expect to be below 1% measurement of the DAO. For ERG, we're going to reach probably 2%. For quasar, between achieve 0.9 and 2, like 1.8%. And for the quasar and alpha, typically 1.1%, which is quite an improvement compared to Bose measurement. Here is a nice spot where you have all these different experiments. We have Bose here in blue, okay, and we have EBOS in green here. Of course, this is much more difficult to find objects and measure them, so that's why we're not going as low as Bose, but very close. And here you have all the future, 5-year, 10-year STEM survey shown up here. So we have Euclid in red, we have DAISY in dark, we have WFIRST in purple, to give you an idea of what will be the name program for the future. Okay, so that's my conclusion. EBOS just started. We've invalidated the approach to a dedicated survey in Sloan 3, and we have already 78 observed. We have also lots of people working on log simulation so that we can do cosmology measurement in the near future. Data is coming in. I want to join. Thank you.
Strong lensing part of your talk. You said that there are no corrections to the theory or so, to what you write down as the lens equation. But of course you know what you write down is more or less the kind of Newtonian analog for photons, right? The Newtonian potential multiplied by 2. Are you sure that there would be no corrections from fluctuations of the density on the line of sight of the photon and things like that? Is that all completely negligible in the strong lensing machine? These relativistic effects kind of.
In principle, yes. Nobody has been looking that into detail, or at least not recently. The only papers I've seen that have been looking at were basically, a very small effect compared to the strong lensing effect we're measuring. I think it would be very nice to revisit that, especially with getting to such accuracy that that was not here 10 years ago when people were looking at that. So I think that's clearly something to be revisited. But from what I've read, it should be fine.
So you showed these beautiful results of finding distant galaxies being magnified by the classical. The issue of that is a bit ambiguous, right? There are some claims that go because high redshift, but then there are low redshift.
Yeah.
And it's difficult to tell until you get
Yeah.
confirmation. What's your take on this? How reliable are these results?
Okay, there's been different kind of measurement of very high redshift galaxies. The one I show, I think, is very strong. Where is it? Okay. Because it's a multiple image system. Previous findings were finding objects at redshift 8, 9, 10, and some of them that have been followed by spectroscopy have been found at lower redshift. There's two examples, one at redshift 10, one even in the frontier field data of an object which was far from the cluster center, supposed to be redshift 8, has been measured spectroscopically, like shown at least last week to be at redshift 1.4. So, but this special case is interesting because it's a multiple image system, and you could not have two images of that color, okay, being a redshift 1.4, because there would be a different location, right? So those systems that are multiple images are very strong, because in those cases, you see other multiple images that are nearby, and some of them we know the redshift, right? So we cannot scramble these. But then it would be very hard to measure the redshift. We might be waiting for the LSD.
Any other comment or question?
There's only two of these things, on over like 10 clusters.